Okay, so yesterday we learned about the plane, the crystallographic plane. And plane, as I said to you, is just simply a flat surface, flat surface. Okay, in a crystal, we can describe, for example, in a crystal, you can describe the plane, describe plane using what we call Miller indices, and the notation for that is HKL. Okay, remember when you have something like this, for example, previously we learned about something like this. I draw a cube. Let's say we take the cubic thing, and then we say before that this, let's say I put this X, and then this is Y, and this is Z. We say before the X, Y, Z is basically a coordinate axis. Okay, and then if you have, for example, from this origin, and then you try to put until the end of the unit cell, we can put it as a A, here as a B, and here as a C. The difference between this is C. This let me put it. Yeah, this is C. So the difference between A, B, C is that A, B, C only stop until here, until wherever you want lah, until the unit cell edge. Okay, but the X, Y, Z is just like the axis lah. So you have this A, B, C, which is the axial length. Okay, it can be half, it can be full, it can be, for example, A can be until here, A can be until the end lah. So it depends lah. Now the HKL, what is HKL? HKL is basically reciprocal of ABC. The HKL, let me put here. The HKL is roughly, we can say it's like reciprocal of ABC. When you describe the crystallographic plane. Okay, so that is basically the HKL. Let me remove this thing, let me make it clearer. HKL. So for example like this, how to find the HKL, how to find the for example, let's say I have, okay, so for example let's say you have something like this, you have something like this, let's say I draw like a cube, like I draw a cube like this, like a cube like this. Wait. Apa ni? Like I draw a cube like that, and then let's say I want to describe this thing. Let's say I want to describe this plane. Let's say I want to describe this, and this. Let's say I want to describe this, and I make a plane like this. Okay, I make a plane like that. Okay, so that is plane, like a flat surface. So now if we see, this is basically the Z, this basically the Y, this basically the X, and also we know here, in order to find the HKL is basically a Miller index. If you look at the top, is a Miller index. In order to find the HKL, you need to find first the ABC. So you need to find first what you do is that first select the origin. So here we can say that we select the origin here in the one in the green here. I put in the green, the green here. Okay, so now select the origin, so I put the green lah, in the green. Second, what you do is basically you try to find what is A, find the ABC. Okay, for example now, find the A is basically on the X. A is basically on the X axis. So we know that A is basically, if you look here, roughly like half, right? So we can say is basically A is half. We can say like that lah. And then B, this A is half. And then let me put here A, let me put in this color lah. A equal to half. And then B, if you look B is what? B is basically this thing. B is basically this. the one that I highlight in blue. So B, if you see the intersect point is at the 1. I mean that the intersect happen at 1 lah, 1 unit cell. So we can say that the B is 1. And how about the C? C, if you can see there, is basically half of 1 lah. Imagine now we are denoting this what we call the cube, the unit cell, as 1. Normally in practice we denote the length of this thing as 1 unit, 1 unit, 1 unit, 1 unit, and also 1 unit. So if half of the unit, we can say half lah, half. Okay, so that is ABC. In order to find the HKL, you need to take the reciprocal. Take reciprocal. So reciprocal is that instead of 1/2 is like 2/1 lah. Take the inverse lah of that, 1/1/2. So you get basically the SKL, you will get 2, 1, 2. Okay, and then you put a parenthesis. The most important thing when you try to describe the Miller index is that this thing, you need to use the parenthesis. Wait, So you need to what we call describe the parenthesis. So here you can see here we use parenthesis. Parenthesis. Don't do like this. This is not right. Okay, don't do like a bracket. Bracket is not right. So for example, let's say this thing, this is not right because there are another version for that. Okay, so we don't use bracket, we don't use this and so on. We need to use parenthesis. Parenthesis, that's one thing you need to know. Use a parenthesis. Secondly, there are no comma. There are no comma. No comma. So basically that's how you find, you describe the plane in what we call in a unit cell. Okay. So that's one example. Let's say you have, for example, if you look here, all this what we call all this plane intersecting at the point. You see it's intersect at the axis. But if let's say the plane is not intersecting, that's you need to what we call, you need to view it as an infinity. For example, I give example. So let's say you have something like this, and then I have something like this, and then still I have something like this, and then let's say I draw like another what we call, draw something like this, and then I draw something like this. Okay, I draw something like this, and still this is Z, this is X, and this is Y. Okay, so if you look here, let's say we choose the origin, we select the origin. The origin is here. Okay, let's say we put the origin there. So you can see for this is intersect at X. Okay, if you look here, it's intersect at X. Let's say I put X. It's intersect at X. So the A is basically 1. Okay, and then we try to see B. Okay, B. So B also is intersect. If you look here at half lah. Let's say we put it as half. Okay, so B is half. But now we look at the Z. Okay, so this is Z. Okay, so we see Z. So the plane doesn't intersect at Z at all. So we can say if this the case, we say that this plane intersect at Z at infinity. Okay, meaning that it doesn't intersect lah, because intersect at infinity is same as you said that it doesn't intersect at all, but just the way how people describe lah. So if you look here, the plane doesn't intersect at Z at all, so we can say that the Z intersect at infinity. So we can say C is infinity. So now when you have all this thing, we take the reciprocal, the HKL. The reciprocal, 1/1 is 1, 1/half is 2, and 1/infinity is 0. So you get 1, 0, 2. So that's how you describe the what we call the plane that doesn't intersect in one of the axes. Okay, so now sometimes you see what we call the negative intersect. For example, let's say I do like this example. Let's say I make like this, something like this. Let's say I make x. Let me put the let's say I draw the cube again. Okay, but now instead of putting this as a instead of this is origin, I make this origin. Let's say now I have this x, I have this z, and then this is y, and this, because if you look from the origin there, let's say I go, this is negative x. Okay, so now this is z. Instead of I taking this as origin, the one that I put before, I put the origin. Now I shift the origin to the right. Okay, so now the x here, whatever coming on the left here, is basically the negative x. Okay, so now if let's say I have this what we call, okay, so now if let's say now if I have something like this, I put half of this, and then I put something like this. Okay, I have something like this. Okay, so now I have the plane there. Okay, I have the plane there. So now we can say that if you look one by one. Okay, now we look at the length at the x axis. So we can see at the x axis. So you can see x axis here. Okay, so it's intersect here. So but the problem now, the x is a negative axis. So it's simply you just put a equal to -1 lah, just like that, -1, and then b. So b is y. So b is y. So you can see here, b is half. Roughly, imagine this half of the way lah. So b is basically half, and then c is also half. Okay. So when you do like this, you find the SKL. So what you do is that 1 over what 1 over -1 is basically -1 lah. So you put 1 bar. Okay, 1 bar. So that's how you sort of like put a notation for negative in the Miller indice. Instead of doing -1, you do like 1 bar. This is wrong. You don't do -1. You do 1 bar and then 2, like that. Okay, so that is basically the way how you do lah. The way how you do this thing. Okay, so this thing. Okay, so basically, that's how you describe a plane. So we learned at the beginning, we learned how to describe the plane, the normal plane, and the second, we learned about how to describe the plane that is not intersect in one of the axes, and the last, we learned about the negative plane. Okay, not negative plane but negative index lah. Okay. So the plane here, you basically also if let's say you have plane 2, 2, 2, 2 to 2, you can divide this by the smallest. You can divide by smallest common denominator. So you can divide by 2, you get 1, 1, 1. This is plane, doesn't have comma, right? Okay. If you have 2 to 2 in terms of plane, you can divide it by smallest denominator lah. Okay. So what does it mean here? So it means that plane 2 to 2 is basically same as plane 1, 1, 1. To give you the idea is that let's show this, what we call the wave star. Okay, let me put here, and then we take goal. Open, goal. Okay, goal. Okay, so we can see this goal. Okay, now let's say I want to take a plane 1, 1, 1. So what I do, I go to lattice plane, and then I take this new, and then put 1, 1, 1, 1, 1, 1. Okay, enter. Okay, so if you look, this what we see last class, right? It seems like strange, right? I mean, why they are not like, I mean, why it's like this, right? Why they are not like sharp edge is because of this. If you look here, the distance from origin is 4 angstrom. This basically coming from the the information inside the file itself, meaning that it says that this thing from this from this what you call, what is the origin, this, let me put here A. Okay, from this what you call, from this atom to this atom, the distance is 4.07825 angstrom. So what does it mean here lah, distance from origin? And how they get this is basically because this, remember, the one that I take here, the one that this C file, whatever file that I take here, if you remember, I take it from the crystallographic, I take it from this COD, crystallographic open database. I take from here. Okay, I take from here. And this crystallographic open database is basically at the experiment by the others. If I go to search and I go find gold, let's say I go gold is aurum AU. We have discussed this, how to use this in the first class on the crystallography. And then let me pick 1111. Okay, so let's say send. If you look the search result, wait for it. Wait for it, so let it find first. Okay, so if you look at the result here, you can see the C file, the crystallographic information file here, is coming from the research. You can see this. For example, if you look here, this a name of the author for this research. They do a research about this control growth of hexagonal gold, blah blah blah, and so on, and then they publish inside this thing. So when they do research, when scientists do research, they find the what we call they already study lah how long from this, what is the distance from this atom to this atom, and and so on. So that's why they get this lah, the value of the thing lah, the cell parameter 4.07. So this cell parameter, this is, if you look here, 4.707, 4.7. This basically the length, ABC. This 90 is basically the alpha, beta, and theta. The one that I explained before. When you have this thing, this is basically between this and this is beta, this is theta, and then this is alpha. We have learned before that alpha, beta, and theta is basically interaxial angle. So if you look at the COD just now, what they show here is that the top one, the 4.07, this is in nanometer lah, in angstrom or nanometer, I don't remember, but whatever the thing, this thing, and this is the angle. So if you look here, the angle is 90. So by looking here straight away, you can see that the angle is a right angle. So it is basically cubic lah. So by looking at this alone, you already know this is like cubic system. Some is not cubic, not really cubic. So because this is the angle of 120. The reason why is because the cubic, the goal assume the cubic system, the face center cubic system at the ambient temperature. But sometimes you need to see also the research. Sometimes they do research to not to find the how the goal, what is the goal unit structure, but they want to find other stuff. Okay. So let me coming back here. So here, this thing distance from the origin here, 4.07825A. I don't know whether this is the length for the entire unit cell. So unit cell is this, the cube thing from here to here. Is it 4? Or yeah, I think that's the deal. I think this, the length is here. So this thing distant from the origin is basically from the origin. Normally the origin you start from the O. Let's say I put here. Okay, you can see this A. You see this A, this B, and this C. A is basically X, B is Y, C is Z lah. C is Z. So the origin is this, the ball that is in white in color there. Okay, so the distance, if you put here 4.07825 here, angstrom is basically distant from this, from the center here, from the center, this ball here. I hope you can see my cursor from here to this one. Okay, to this one. So that is the distance lah here. Okay, so the reason why I don't get like the sharp edge is because this is 1.7. You just put 1D lah, 1D, 1 distance, and then you can get like what you see lah. This now is correct lah. Okay, so let me put A. So this is normally how we look. Okay, so this is 111. Okay, so if you look here, this is the correct one. If you look here, the plane, the slicing the what we call slicing the atom. Okay, so it must be on the atom lah. It must be the plane should be where the atom is. Okay, so where the atom is. Okay, so this is plane 111. Okay, we have learned before. If let's say you make this bigger, let's say I make this bigger, I make this bigger, I make it 3, 3, and 3, and 3, meaning that I expand this structure so that there are 3 on top, 3 on the side, and 3 on the bottom. You will get like this. Okay, so you can see the plane still 111 like that. So if I make this thing, edit lattice plane, and then I make a new plane, but still I want to do let's say I do 2 to 2, 2 to 2, 2 to 2, 2 to 2. This is 1. Enter. Okay, enter lah, enter. Okay. So you can see 2 to 2 is just half lah, actually half. 2 to 2 is basically half. Okay, so the 2 to 2, let me change the color. It's much easier to see. Like this plane, I change the color for this 2 to 2. I change the color with how to change the color. Let's see, can I change color here? Okay, let's say, okay, so you can see the 111 is basically in the pink color. The 111 is pink color. The 222 is the same as what we call 111. Okay, the plane is almost the same. Okay, why they are smaller is because it's reciprocal. Remember, it's reciprocal. So if 111 is like this, you look here. Okay, so for example, let's see, you can see here 212 here, 212. How is look? It's look. You can see at the x is half, half, and half. If the y also at the half, then you get 2 to 2. Okay, so basically that's the reason lah. But this plane is no use lah. The plane at 2 to 2 here no use because there are no atom there. So it's not really useful for the research whatever lah. So this 111 just to denote that this. But if I go to okay, so if I make a new plane again, and then I put 111, 111, 111, 111, and then I put number 2 instead of 2. Enter. Okay, so you can see I got the second plane there. Second plane. Okay. So you get this plane. Okay, let me remove the 2 to 2 at the beginning. Edit lattice plane. Let me remove this thing. Delete. So okay, so you can see here the plane the plane here, the triangle plane, is basically the plane that is the green and the pink. If you want to describe that in the what we call in the Miller index, you can describe it by 111 also. Okay, it's the same. Okay, it's the same. Okay, so you can also go further by, for example, let's say lattice plane, and then I put another 111 new, put 1 1 and then 1 and then 1, and then I put instead of I put 3D, meaning that, what does it mean by I put 3D? Meaning that 3 times the distance of the original unit cell lah, because unit cell as you can see just now, 4.07825 is basically the length, the maximum length of that cubic unit cell from the origin to the edge of the unit cell. So 3D meaning that as if you expand the unit cell to become 3 times bigger. So that's what does it mean lah. So next I make it 3. Okay, so let me put the color different. Let me put in red lah. In red. Okay. 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 So you can see that there are 3 plane. There are 3 plane. All plane is 111. The pink is 111. The green is 111, and the red also 111. Okay. So what is important about this? What is the takeaway about this is that the plane, the parallel plane always have the same Miller index lah. The parallel plane, okay, all these 3 is parallel lah. So we can say okay, so we can say that parallel plane, parallel plane have similar Miller index. Okay, so that's the takeaway thing lah from this. And also the distance between plane, if you see, there are 3 planes. They have the same distance, is equal distance, meaning that the distance the distance between the what we call the pink plane to the green is d lah, is distance lah, is the same as the distance between this, the what we call the pink and the green is the same as the green and the red. Okay, so if you increase the plane to the next plane and so on, the distance will be the same. So one of the thing that you need to understand from this plane stuff is basically the plane, the parallel plane, have similar distance with each other. Okay, the parallel plane have a similar distance with each other. So the parallel plane have a similar distance with each other. Okay, so now you might ask why we should learn about this plane at all. What is the purpose? What is the useful of learning the parallel plane, the plane and this stuff? The reason why this is important is that, do you remember when you do the assignment for this what we call for the SRD, I asked you to sort of like to find to give some of the what we call the example of the SRD pattern. So some of you draw something like this, something like this, and if you realize there are sort of like number here, 112, 113, 114, whatever lah number, there are number lah in the bracket. Let me see if there is other in the So if let's say I put a SRD pattern, SRD pattern, so image. So if you look there in the SRD pattern, you can see that, for example here, I take this, you can see there are the Miller index there, 111, 200, 220, 311. So this all is basically the plane lah. Okay, so why this plane have this? So you know this, what does it mean by this image is that at plane 111 and at plane 200 and at plane 220 and at the plane of 311, there is a what we call constructive interference lah. Constructive interference, because this relate to the what we call this distance, what we call this thing, if I can, because this relate to Bragg's formula, Bragg's formula in XRD, SRD. I asked you before to learn about SRD. So SRD is a machine to sort of like, you have sort of like a sample here, and then you shine the X-ray, and then the sample will sort of like reflect, the X-ray will be reflected, and then they will be give some result lah. So let's say this sample, so basically the SRD more or less like this. Okay, so the sample here, usually we are what we call, we are analyzing the crystalline sample, because for example, why the reason is that, imagine now this sample here, imagine the sample here, it's like this. Okay, imagine the sample have the atom like this, the atom, and then there are atom. Okay, let's say these two atom, that not this is part of the atom, there are a lot more lah, lot more, and so on lah. Okay, so we learned before about the plane. So the plane is where the atom reside online. So this we can view it as a plane lah. This plane as a plane. Okay, we can view this as a plane. And we said before, if the plane is parallel, it's the same plane lah. If the plane is parallel, then we can describe it with the same, what we call same Miller index. So this plane, if you see, is parallel. And if you see here, the distance between here and here is D, and here is D. Okay, so once you know the D, the distance between atom, then you can back calculate where is the atom in the space. That's what the reason why you want to find this, why you want to find D. D is simply what we call a distance from one atom to another atom in a plane. So that is D. So once you know the D, then you sort of like can back work where is the atom in the space. Because in a crystalline material, remember, in crystalline material, things repeat again and again and again. So if let's say I have another plane at the bottom, let's say I have another one here, because it's like repeating, right? So there also another plane here, which is the same plane in terms of Miller index. This also D. The distance between this also D. So that's the reason why you want to find D. Okay, when you shine the what we call the X-ray, let's say the X-ray go here. Okay, let's say you shine the X-ray here, pop like that. Okay, so when the X-ray go meet the atom, then it will be reflected lah. In this case, it will be reflected. Okay, let's say there are another thing, and then it will be reflected like that. Okay, let's say this is X-ray lah. X-ray. This is X-ray. This is what we call incident X-ray. X-ray. This is what we call reflected X-ray. X-ray. Okay, and we know X-ray is what we call is a wave. It's a wave. So the wave, you know, is like a. So the wave is somehow something like this. You have something. So imagine now the wave. Okay, so if you look at the, let's say I put this A, let's say this A, and then this B. Okay, So there are two wave of X-ray. Imagine in the reality there are multiple wave lah, but I just draw two so that much easier to understand. So they are A and B, and by looking at this X-ray, we know just by looking it, we know that B is longer than A. B is longer than A. We also know that the X-ray is a wave. So let's say we draw a wave, something like this, like that. Okay, something like that, and then reflected also something like this, something like this. Okay, so that is for the A, and we learn the wave can interfere. Okay, we learned also before wave can interfere, interference of the wave. Okay, what does it mean is that if you have wave like this, you plus with another wave like this, what will happen? Will become bigger. If you have something like this, and then it become smaller. If you have some wave like this, and then emit the wave like this, it will sort of like destructive. So these two things, the one become bigger and become smaller, twice smaller, we call it this thing, we call it constructive interference, and this thing we call it destructive interference. Okay, so now, so this, you see, we only talking about one wave now. In order to make constructive or destructive, we need to think also the second wave here. Okay, so but before that, let me put this thing. If I can make like what we call this thing, okay, so let me put this so that it become parallel. So if let's say I put another this thing, let's say the wave normally in parallel lah, so it will be same, okay, and this also same. Because remember, the wave come in one go. The X-ray wave come in just one go. So it's just one wavelength lah, one phase. So that's why it's the same as the top here. This is the same. This the same. This same and top. This same. This also same. But now we have extra pass here. Okay. In order to make the what we call, remember this thing is what coming out. Okay, in order for this blue, the one that I highlight in blue, is similar to the one that highlight in green. Okay, in order for this blue and green to be similar, whatever happen in the middle here, in the yellow area here, must be will be full wave lah. So for example, let's say I put here, if I do like this, then it can be like that. This is like full wave lah, full wave. Okay, so if I try to make this like this, if I try to make this what we call the center, and I take this out, so let me put outside lah, easy. So let's say I do like that, and then I do like this, so to make clear lah, so I do like this. Okay, so if you look here, this thing, I take whatever here, I put outside. So when you shine the X-ray, you shine in certain angle. For example, this angle. So let's say this angle, let's say theta. I put the different color lah, difficult, this color I put in red lah, in red color. So this is theta, because when you shine the X-ray, you shine into in angle. So this theta, using geometry, using the geometry, this also theta. I mean, you try find your ways lah. But basically, when you shine in this angle, the angle here also come theta. Okay, it's the same. Okay, so that's geometry lah, geometry. Okay, so now this thing, whatever here, between here and here, is D. Because yeah, you can see D, D is D. Okay, and then this whatever in the green here, this is basically the what we call whatever wavelength lah, the wave. So we can put it like wave lah, wave. So this is wave lah. So let me put it in the drive. So this is basically wave lah, in the wave lah, wave. Okay, wave. Yeah. Okay, let me draw here. So this is thing lambda. Okay. Okay, so now the purpose of people doing SRD, the main purpose of people doing SRD is to find what is D. That is the main purpose. The main purpose to find what is D. Okay. So now to find D, this is a right angle. This is right angle. So you know from the trigonometric, sin theta. Wait, let me put sin theta. Sin theta, it become sin OH, opposite hypotenuse. So basically sin theta is basically the lambda here over the D, over D. What is D? D is red, green, over D. Okay, so that is basically the thing lah, sin theta D. Okay, so you can just rearrange the thing. You will get, rearrange this thing, you get lambda equivalent D sin theta. You get that, lambda D sin theta. But because now we only consider only one what we call one right triangle. Wait, this. Okay, now we only consider one right triangle. But if you look here, you can see there are two right triangle. There are one on the left and one on the right. So it's basically, you are basically do it twice lah, because the theta here, because remember there are one theta here. If you consider there are also another theta here, so you are duplicate. So that's why they are sort of like, you do like lambda to D sin theta lah, to D sin theta. Okay, so this you get something like this. Okay, so now I want to talk about this lambda. If let's say this, in order for what we call, in order for the wave, the reflected wave to be similar to the reflected wave on the top, whatever in this yellow region, the wave must be sort of like full. I mean that it must be full in order to get. What I mean here is that wait. Okay, so for example here, so in terms of wave here, if let's say this part you have like something like this. Let me put wait, I need to, okay, wait. So this, the full wave, we call it full wave lah. If I have like this is full wave. They are one cycle. Okay, this is one cycle, and then let's say I put like dot like this. This one cycle, and then if I continue another one, another cycle, we put green, another cycle, and then if we continue again, let's say I put in green, you have the third cycle. Okay, so in order to get what we call the bottom reflected is equal to the reflection of the top, the cycle must be full lah. This thing, one lambda, we call it lambda. This what we call another lambda, and this what we call another lambda. Okay, so as long as the what we call, as the lambda is full, I mean the integer, in integer mean that there are no fraction, because what does it mean? This is one lambda, so in total we can say in total is 3 lambda lah, 3 lambda. That's what does it mean lah. But if let's say you have something like this, let's say you have something like this, and then you have a wave that is not fully something like this until here only, until here only. So this is basically half lambda. So this is basically half lambda. Okay, so that is fraction. In order to, for example, you to get back the same reflection to the top, this thing, whatever in the yellow region here, must be in full integer, meaning that it must be complete lah, either lambda or 2 lambda or 3 lambda or so on. So that's why when you see the Bragg equation, you have n here and there is like integer lah, integer. So this, whatever this thing, if you remember back what you did in your, what we call, in your SRD assignment, this what we call Bragg's equation. Bragg's equation. Okay, Bragg equation. Okay, Bragg equation. Okay, so the purpose of Bragg equation is basically to find what is D. Okay, so so Bragg equation can only satisfy, okay, Bragg equation here can only satisfy if this lambda is whole, whole number, okay, whole number lah. Okay, Bragg equation can only satisfy, okay, let me put lah, Bragg's equation can only satisfied if the lambda is whole, meaning that n equal to 1, 2, 3, so on lah. Okay, so only then you can get something like this, and when you get only then you can get something like this, and once you get something like that, when you get something like that, you know it's constructive interference. Okay, constructive interference. So constructive interference, what you get a peak lah, intense, because remember constructive interference is basically a mixture of the, what we call, of the wave lah, mixture of the wave that is constructively interfere. So that's why if you look at this, let me open this thing. If you look at this thing here, the one you see that is what we call in the peak here, let's say this 111, we learned before 111, what is 111, right? So meaning that here, for this sample at this 111, plane 111, they are constructively interfere. But here, the one that is not, they are peak, there are no interference lah, there are no, it's either destructive lah. For example, here they are nothing at all, mean that they are destructive interference here. So they are destructive interference. This, the one that is peak, is constructive interference. So once you know the, what we call, the angle, you see at the bottom here there are 2 theta here, the angle, we know about the angle, right? The angle, and also you know also the plane, the Miller index of the plane. By this you already know what is the D, the distance between the atom, and you can know the distance between atom of plane 111, because remember plane 111 and plane 200 is 2 different plane. For example, let's say I go here, this is plane 111. Let's say I make a plane, let's say I make plane, edit lattice plane. Let's say I make plane 100, new 100. Let me put in the color, maybe in blue. Okay, and then okay, let me put another one, new, and then this I put 2. Okay, enter. Okay, if you look here, if you look at this image, The one in triangle there, I use different hand, so it's difficult. So if you look here, how to? Okay, if you look here, the triangle plane is 111, but the plane in blue is 100. If you see here, blue, let's say I take blue, I take blue. This is 111. Okay, so it's blue. You can see the distance between this blue and this blue, they are longer. They are longer than the distance between this and this. If you look here, this D, distance between plane here, the distance between a plane 111 to another plane of 111. So you can see the distance is quite not too big. There are no middle atom in the middle. But if you look blue, there are atom in the middle. Why? Because you see here, the reason why this plane, because this is different plane. If you look the blue, if you look here, you can see from the side, from this, it's difficult to see, how to see. You can see this. You can see the distance here is different than the distance that we see just now at between 111 plane. So that meaning to say this thing at 111, the distance is different. If you find the D from here is different D of here, the distance also different here, because this is distance between 200 plane. This is the distance. If you calculate using Bragg equation, whatever here you get the distance between 220 plane, okay, and so on. So once you get the distance for each plane, you sort of like can map in the space how this you can put together in the space. Okay, this is where, this is where, this is where, and that's the reason you will know how the material in the molecular level, where the atom sit in the space. Okay, so that's the reason why when you sort of like, why you do SRD. The purpose of SRD, X-ray crystallography, is because to sort of like to know the distance, to find the distance, because once you get the distance here, you know what we call the atom lah, the atom. So if you look here, this is the what we call the example of SRD for crystalline material. Okay, it's sharp. You can see it's very sharp. So for crystalline material, normally for SRD you get something like this, something like sharp like that, sharp like that, like that, and this whatever plane. But if you have amorphous material, you get something not like that, but you are rather get something, maybe something like this, something broad. We call broad, not sharp. Why is broad? Is because this is sharp. The reason why this is sharp, because it's intense in terms of what we call because the wave, the X-ray wave will sort of like interfere constructively, very exactly. This will exactly go like this, and then you get bigger. That's why it's sharp. This one, maybe you get like this, and then it will maybe shift a little bit. Maybe it's not like that, and then you got in the middle lah. Not very in terms of what we call intensity, is not very sort of like as high as when the what we call this two wave interfere perfectly with each other, top and bottom. Okay, so that's why SRD is only used for to analyze crystalline material, because if let's say you cannot do SRD for water, because in water the molecule move here and there, so you cannot get you cannot really sort of like put the water molecule fixed in one position. So that's why people don't do SRD for liquid. People do SRD for solid only. Okay, for solid only, for SRD for solid only. If let's say people want to find what we call the atom position, for example the liquid thing, for example like water, they need to freeze first. Okay, so you have SRD for ice. You can do SRD for ice because ice is frozen, meaning that the water molecule, the H and oxygen, the hydrogen and oxygen will fix at one space, so they can sort of like measure the distance between the plane, and also back calculate where is this and this. But you cannot do SRD for water or any liquid lah, because the purpose of SRD is just because SRD depend on the plane and also to find the D and so on. So you cannot do SRD for liquid lah. In order to understand the liquid, you need to freeze that first. To freeze that first. Okay. So one last thing before we end, I invite you to sort of like see this thing, feedback interference. Okay, so this fact PHET is basically one of the simulation developed by University of Colorado, if I'm not mistaken. So let's click here. So what we call, you can see lah what does it mean by interference wave here. So example wave here, if you click here, you can get this thing. For example, let's say we are talking about the X-ray. So X-ray is light, so maybe we take light. So this is light lah, light. Okay, so but here there are no X-ray lah, it's just a color lah, light color, but it doesn't matter. So just to show you what does it mean by interference, you click here, they show you the wave of the light, and then you have this thing. So what will happen is that it become like that, and then if I put the screen here, you can see the graph, and not the graph here, screen intensity. See, okay. So basically when you have this, what we call, let's say I put here, the graph that you see, the one that you show, you see in the SRD and so on, this lah, the graph, the whatever this thing. So if that intense, then you have this peak. Okay, you can play around lah this, whatever amplitude, separation. If you sort of like this, they are make a big difference. So you can see the graph, the graph here. You can see this like this and so on. They are different. You can play around. So just to show to you, whatever here, whatever you see just here, the graph here coming from the interference lah. This thing, it's just intensity. Okay. So I want to show this diffraction thing. Okay, diffraction. Okay. So imagine this is the top one is the light, whatever light, and this is the sample in the middle. This is the screen. So if you shine the thing, you get something. So this thing is 2 dimension. Whatever this pattern is 2 dimension. But sometimes you see also when you talk about the SRD, especially for the single crystal, normally they use the SRD not pattern, but they use SRD picture, SRD image. Okay. Sometimes you see photographic image, single crystal. Okay, so for single crystal, normally they use picture like this. You will see picture like this rather than the what we call the peak like that, the pattern. Okay, so something pattern like this lah, pattern, the one that I show you in the class when I bring the compact disc and also the laser. Okay, so that is basically SRD image lah. What you see just now, the one that is sharp like this is pattern. This is pattern. Okay, normally for to get this pattern, normally you get this pattern normally when you deal with the polycrystalline sample lah, something that is not single crystal. But if you have sample that is single crystal, it's much better to use the picture like this, something like you get the picture like this lah, whatever picture like this. It's much more accurate. Not accurate meaning that you get more information. this also okay. You can, this and this is a photographic plate lah, and normally for single crystal, this normally for powder lah, powder diffraction. They got it's much easier to analyze using like this lah. But for single crystal, this is much more easier to analyze. Okay, this for not a single crystal, polycrystalline crystal like a powder and so on. So it will be more, it will be very what we call very messy if you put on a picture like this. But because this is single crystal, that's okay. So I just need to show you, if you put a light here, you can just, if you make smaller, you see the different, and then if you make a cube, you get something like that, and then if you make like this, you get something like this. Just to show you this, for example, if you look here, this is like a crystal light, like a crystal. You can see they are sort of like the atom. Imagine the white dot is the atom. So the atom is on the very specific, very what we call, they have pattern there. You can see there are pattern. They are, the distance between this and this is same, and the distance between this and this is same. So we can see there are pattern here. So we can say that this represents sort of like crystal lah. So if you shine the, what we call, shine the you can see sort of like very clean, very intense this. But if you try to change the, you can see here bottom here, you can see disorder. If you try to increase the disorder, you see what will happen. So this represent the amorphous material. So you can see it's much difficult to, what we call, to sort of like to study, because when you have this order, because if you look here, how people find the D from picture, just now we learned how to people find D from the crystal plane, right, 211 and so on, using Bragg formula. But here also you can find the D by measuring the intensity. This and this, they are what we call, they are, people can calculate, people can take a ruler and then measure from here and here, from here this intensity to this intensity, and make make the what we call this interpretation. So that's how people do lah. So that's why when you see the photo 51 is basically this photo 51, this thing, the one that you see just now here in front of you. I want to take the picture image. Okay, this photo 51 here, this is basically the SRD of the DNA. Okay, you can see like the X, right? So using this image, scientists can deduce this X is basically people know when you have this X pattern, the sample have sort of like the double helix structure. Okay, so you can see here how this they analyze, they analyze the what we call the double helix, this double helix and so on. So using this what we call this SRD, X-ray, in this case they use the photographic plate instead of the pattern. So you can see, you get more information, you can get this X and so on. Okay, so this is basically how they analyze lah. So you can see here how they analyze the so you can just Google this thing, how they analyze, how the DNA, the distance between DNA and so on. Okay, so basically you can look at this wave interference and try to play around lah, because you can see if you make it bigger, you can change, and then you can see the different. So yep, and then you put the picture, you get something. So this is like amorphous, okay, so that is the picture of the human, and you see there are no pattern, there are no like repeating pattern, right? So you can see what the SRD give you. It's so difficult to understand, and then yeah, you cannot really work on it, cannot. Yeah, so that's the reason why SRD only useful if you have something that is repeated like this, so you can sort of like find the ways and so on. So I think that's it for today lah.